Welcome to today's webinar, where we will be exploring how measured heat loss can be used to optimize heat pump design. Not only does this give installers the most accurate results for their clients, but it saves them both install and running costs, potentially totaling thousands of pounds. Today, we are joined by Richard Jack, Technical Director here at Build Test Solutions, and Leah Robson, who is the MD of Your Energy, Your Way.
Thank you, Tanya. So today we're going to have a little bit of building physics because it's everyone's favorite topic, and some worked examples around heat pump sizing. And then I'm really excited that we've got Leah on to have a real expert on heat pumps to give an installer's perspective, and then we'll have a good bit of Q&A. And I've got some burning questions I want to ask as well, so I'm going to steal the first bit of Q&A with some of my own questions. So what you've all come for is building physics, clearly. So I wanted to think about the way heat comes into and goes out of a building, and use that as the basis to hang a little bit of chat around what a heat pump calculation is, what a measurement is, what the difference is, and how they could work together. So here's a super simple model of a building, and we've got some heat inputs on the left-hand side. So solar gains, fuel supply, electricity use, occupants, so they're creating heat inside the building, and then we've got our heat losses on the right-hand side. And when we do a heat loss calculation, the method is we take each of the heat loss paths and we estimate the performance of that bit of the building, the roof, the floor, the walls, the windows, the doors, how much air movement there is, and we estimate its U value, so some factor about how well or poorly it resists heat transferring through it. And we estimate the amount of air movement, so by ventilation and also by infiltration. We multiply our U values by our areas and we add them up, and that gives us the amount of heat loss. Okay, and I think that is a simple to understand and totally logical thing to do. So why am I suggesting that we ought to do something different? What's the problem with that? Well, the problem is that real building performance is incredibly variable, and the more measurements that our users do, the more firmly convinced I get that buildings are weird and wonderful, and the ones that you think are going to be the same just aren't. So in this slide, we've got a number of different factors about building performance and how much they vary when people have done studies of them, people have done measurements of them. So I've picked out in the top row there the air tightness of just semi-detached buildings, and that is from our database of pulse air tightness measurements, and there's around 13,000 semi-detached buildings, so it's quite a big sample. And the amazing thing is they have an average air tightness of about 9, but the variability of them is, you can see there on that chart, 82%. So when I go to look at the next semi-detached building, I know that the average air tightness of semi-detached buildings is around, it's actually about 8.6. But it could be 82% higher or lower than that, just because buildings are dissimilar to each other. They're variable. And it's the same for U values as well. So we look at some new build there. New builds have low U values, so they're in the 0.2s and 0.3s, which means any difference is a large percentage. So the percentages are perhaps a little bit overblown there, but it just shows you that they are super variable as well. And in fact, every parameter about a building, when you get a sample of measurements, you find out that it's really variable, even for buildings that look the same and you think must be the same, they're not the same. So when we go back to how we do a heat loss calculation, we look at a building, we see what it's made of, and we assume a performance level. What we learn from this is the best we could hope to do is be right on average, but variability of buildings means that it's just impossible to be right for that particular building without measuring it in situ and finding out that particular building. And I've used this example for years, so apologies if you've seen it before, but I think it just ties together that really nicely. So here, I was measuring the heat loss on this cul-de-sac in the middle of this Google Maps view. And I measured the heat loss of 10 buildings of the same design, same build, same council owner. Same builder, almost certainly. Um, have been in place there for around 60 years at the point I measured them. So if you looked at the buildings, they are the same. They're not different to each other. And if you did a calculation, you would calculate the same amount of heat loss. But when you measure them, you found out actually that the building with the most and least heat loss were 100% different to each other. So actually, in this case, the calculations were right on average, so within 1% of the right amounts, but each individual building varied to each other. And so this enormous amount of variability, even within the same building by eye. So what things can we measure about these buildings to find out how much heat loss they've actually got? So I think in layman's terms, I decided to say you could either measure it bit by bit, or you could measure the heat loss altogether. So when you do bit by bit, you think about each of those assumptions that you've made in your heat loss calculation. And instead of assuming what the performance is, measure it, plug it into the heat loss calculation, and you're calibrating your model to match real life. So the things we could measure there would be U values. U value measurement takes each element. So if you wanted to do a floor, a wall, a roof, and you had one kit, you'd be talking about 3 hours of measurements. Or if you had several kits, you could reduce your time. And air tightness measurement takes just for the measurement itself, perhaps around half an hour. Might take you longer if you need to measure up the building. That's often the measuring the dimensions, often the most time consuming bit. Similar for measuring ventilation flow rate, so how much air is actually coming through those fans. And that's important for heat loss, but also just checking that you have enough ventilation. So you can measure each of the bits individually, or you could measure the overall heat loss, the heat transfer coefficient, so the total heat loss using something like Smart HTC. That requires 3 weeks of data. The measurement, the sort of time involved as an operator is relatively low. So perhaps around half an hour to install sensors, but you do need those 3 weeks of data. You could either use smart meter data and temperature data, and that will give you the best possible gold standard precision. Or you could use Smart HTC Go, and that works only off smart meter data, so that you could do that measurement based on past historical smart meter data and have it pretty much instantaneously. So here's a worked example of a fairly standard looking mid-terraced house. And here I've got the difference between the predicted heat loss and the measured heat loss. And I've used these bit by bit measurements to define where the differences come from. So the right-hand side marked subtotal is the performance gap, the total difference between predicted and measured heat loss. And you can see that our bit by bit measurements, I call them diagnostic measurements, are telling me where the difference is. So I've got much less heat loss in this building than I predicted. Most of that is coming from the external walls having less heat loss than was predicted. Also, the party walls having less heat loss. A few bits, though, were worse than predicted. So the heat loss through the roof was worse than predicted, and there was more ventilation than predicted. So debatable whether you call that worse, but there was more air movement. Air movement's important, so it's not necessarily a bad thing. But so you can see that the altogether measurement tells you how much heat loss there is altogether, but doesn't tell you where it's going. And then those bit by bit measurements tell you where that heat is going. So the calculated heat loss was 210 watts per Kelvin HTC, so 210 watts of heat transfer per degree of temperature difference between inside and outside, and for that region would have led to 5.1 kilowatt peak demand. The measured heat loss was 127, so significantly less. And that was our goal, to figure out what's the overall heat demand. We could have stopped there. Didn't in this case, and did those extra measurements. It explains the difference, which is helpful not just for heat pump sizing, but also just for understanding the building and what would be good fabric measures to do to it. But the other measurements also help us to calibrate our room by room heat loss, and therefore what size emitters each room needs. So you get a little bit extra from it as well. So that's one particular building. Now, I wanted to talk about a project we did where we looked at 80 houses, really different types of buildings. So there's some old builds, some new builds, and some in-between builds. And we compared the 12831 calculated heat loss with the measured heat loss for all of those buildings. So each bar on there is a home. And you can see that almost, for 68% of the houses, the calculation was wrong. So significantly more than half the time, the calculation calculated the wrong amount of heat loss. It was far, far more common for the heat loss to be overestimated. So for 60% of those 80 homes, heat loss was overestimated. But there are also 8% of those homes where the heat loss was underestimated. So it can happen both ways round. We hear a lot, I think, when people talk about measurement, basically saying that calculations oversize heat loss and you can downsize your heat demand by using a measurement, but it's not always the case. Buildings are weird and wonderful, and some of them have more heat loss than we think as well. So quite a big sample of buildings there, and you can see that there's a clear difference between the calculation and the measurement, and that is all to do with that variability in each of those parameters that I talked about earlier. We also, I haven't shown it here, but we did a sort of a secret shopper activity for around 5 of the buildings in this subsample, and we got 3 different heat loss calculations from 3 different providers for the same 5 houses. And I could present that the calculated heat loss varied a lot as well. So the assumptions that are used are not always, and heat loss calculations have their own inbuilt variability. So does right sizing matter? This is an AI depiction of a Goldilocks perfectly sized heat pump. There's a steaming bowl of porridge just outside the shot that I had to cut out because the AI generated text was complete nonsense. So does right sizing matter? Well, I think this is a question that I definitely want to ask Leah. And I wouldn't class myself as a heat pump expert, but I think it means that oversizing or that undersizing has a big impact on install cost. The heat pump is going to be a different size. Bigger heat pumps cost more. There's going to be more emitter changes required, probably, if the heat demand is thought to be higher. Pipe work changes to go with it. So I think it's a big impact on the install cost and on the disruption of the install. I think it impacts on running efficiency, but I never like to make that statement declaratively and with total certainty, because honestly, I don't think it's been proven well enough. And I also think that it has an important role in minimizing the risk of undersizing the heat pump. So those 8% of houses where the heat loss was undersized. So I think this is a big risk management benefit as well. So that's a bit of background on heat loss measurements and what's involved. I'm going to hand over to Leah now to give an installer's perspective.
Hi there, can you hear me okay?
Yes.
Good, excellent. Okay, so I run Your Energy Your Way. We've been in business for 8 years now, and I've been installing heat pumps personally for 12 years now. So I think I'd like to start with a bit of a plea on behalf of the installer, because I guess you'll have gathered from Richard's presentation, this is actually really hard to get right. And there's a lot of criticism, I think, out there of installers. Oh, they're just always oversizing heat pumps. And if you are cautious and new to this, then it is very tempting to oversize heat pumps. And we'll go into this why a little bit more, but it's much more of a danger from an installer perspective if you've undersized a heat pump than if you've oversized. So if you're looking at your bottom line and you want to make sure your customers are definitely warm, it's always going to be easier to oversize. So I think I think this is something that is an inexact science without the measurement tools that Richard's described. And it's not easy to get right, and only over years do you kind of gather a feel for what you think is going to be the heat loss of a building that kind of keeps you in check. But no, it's not an easy thing. How do I move forward? Sorry. Oh, brilliant, perfect. I just say yes please. Right, perfect. So yes, I just want to tell you a little story about 2 of our customers. They live in a 1930s detached 4-bedroomed house, and they are scientists by background. So we do not approach every heat pump install like this, only some of them. And this one particularly, they were very interested in the science and the data behind having a heat pump and solar panels actually fitted. What you can't quite see on this picture of the front of the house is they do have a small rear extension that was built about 10 years ago. So, but other than that, the house has good loft insulation, mostly double glazing, 1 or 2 secondary glazed windows, but no other insulation. As you can see, they've got an integral garage, they've got tile hung at the front. So it's not a brilliantly well insulated house. Just moving forward. So we did a number of measurements on this house. We started off with the conventional heat loss survey, as Richard has described, adding up all those different sources of heat loss from the building. And we came at a figure that would have led us to put in a 12 kilowatt heat pump. So I think we were somewhere around the 10 kilowatt mark. And then we also, for this reason only on this particular project, because the customers were interested, we also put in the data loggers that Richard mentioned. So you can see one of the loggers here. The downside of this for heat pump installers is that they must have a significant temperature difference between inside and outside while they're in the home for 3 weeks. So we are definitely now out of data logger season. So it is a winter activity, unfortunately. But that actually, once we did that, that gave us, and I'll come on to this on the next slide, that gave us quite a different answer to the heat loss. We also carried out a thermal imaging survey, and actually, I don't know if you can make this out too well, but this is the beam, this is inside their kitchen with the extension. This is the beam that was the old external wall of the house, and this bit here is the new extension. So this is quite interesting, and actually caused us a bit of a problem because I didn't pay enough attention to this image when we did the thermal imaging survey. I'm trying to give you a warts and all version of the story here. So I came back to this later and realized this, but at the time, this is an older bit of the house. This is 10 years old. I made the assumptions about the U values of this bit based on the age of the extension. And actually, when we'd done all our measurements, did our install, everything's working perfectly, except that this room, we did not put a big enough radiator in. And when I came back to it, I looked back through and realized that something is obviously not right with the insulation in this. So that's a bit of external sealing. Something has gone awry there. And that actually led to the kitchen being a lot colder than my calculations made it. So yeah, I guess just to illustrate, these things can catch you out in nasty ways. So yes, we did the data loggers, we did the thermal imaging survey. I have to say, generally, we don't find an awful lot of useful stuff from a thermal imaging survey. It tends to throw up structural things that people can't really do an awful lot about. But in this case, it did give us some useful information that I missed. We also did an air tightness test. So we used the door blower test. And this one, as Richard mentioned, obviously, there's a lot of variation in air changes between different properties, even of the same age. But this I find really interesting for the customers, because our customers really like going around the house and experiencing where those drafts are coming in. And then most of the time, they're really simple to fix, things that they can sort out, often themselves with some DIY or by getting in somebody to fix the air tightness issues. So just find it a really good kind of exercise to take out with customers, but it also, of course, gives us useful data towards the heat loss of the building. So I think the next slide has got some of our results. So having done our conventional heat loss, yes, that's it. So we ended up with 9.31. That's with the calculation rather than the measurement. So that's making assumptions about all the U values and the air tightness and everything. So that would have meant that we would put in a 12 kilowatt heat pump because of the steps of sizes that heat pumps come in for the particular brand that we were going to install. The data loggers painted a very different picture. So this is the report that comes out of the data loggers, and there is a confidence interval. And even if you went to the very top of the confidence interval, it was still significantly lower than where we'd come to with the heat loss. And bearing in mind, this is a relatively old, not terribly well insulated property. It was a little bit too much of a leap for me as an installer to suddenly go in and say, well, let's just put in an 8 kilowatt heat pump. Of course, we'd also done the air tightness test, and that actually came up really pretty low for a house of this. I say for a house of this age. Typically, we find that any house that has wet plaster rather than being done with dot and dab tends to come up pretty airtight. That's my observation, not based on many. Well, yeah, based on quite a few measurements. So also, we've done the Then the next step, given sort of the uncertainty and obviously the risk as a heat pump installer to go in and put in a much too small unit. I had a chat with Richard, and he brought along his clever tool. Is this the right name for it, Richard? Your infrared U value measuring tool. I think that is correct.
That's correct. We call that product name Heat 3D, but that is what it does, yeah.
Heat 3D. Okay, all right. So you can explain the science, but in layman's terms, you point something at the wall for an hour or so, and you work out at that point what the U value of that particular wall is in that area. And interestingly, these were solid walls, and the U value came out between the two places that Richard measured, came out at 1. Now, that is way below the U value that people normally assume for a solid brick wall. There was a little bit of variability between the two spots, but that gave us the confidence, combined with having done the data loggers, to realize that, yeah, we could go for the 8 kilowatt heat pump rather than the 12. So on the next slide, it's just kind of a so what. I've just put the different sizes of the two heat pumps onto this. So the customers, although it does look like they've got quite a lot of space out the back there, this is their seating area. They were quite concerned about having a really large unit. So this unit is just under 1 meter rather than 1.2 meters, and height-wise only 85 centimeters rather than a meter tall. So some reduction in size, which is a consideration for customers. Not in this particular case, but sometimes we're really struggling. We work a lot in and around sort of southwest London, very urban, built-up area, and often we're struggling with the sound calculation that we need to do. So being able to have a smaller unit can often mean that it's easier to meet the sound calculation because they're quieter. I think for me, the biggest impact here was really about the radiators. So in this house, in the end, we only upgraded 5 radiators in the property instead of the 12 that we would have needed to upgrade based on the 12 kilowatts worth of heat loss. So roughly, given the different size of heat pump and given the radiator install costs, I would say we reduced the cost of that installation by at least £2,000, if not a little bit more. I wanted to have a little look at the running efficiency of the heat pump to show you something, but unfortunately, these customers keep their house at 17 degrees. By choice. It's not that the heat pump can't heat it properly. So although I do have data on how it's running, and it's running at a very nice SCOP of somewhere around the 4.8 across the year, that's probably cheating a little bit because it was designed to run at 21 and it's actually running at about 17. So I found the coldest winter day that we had this year, and typically the heat pump flow temperature was somewhere around the 40-degree mark, which is a really nice, low, efficient heat pump flow temperature. So this particular example is running very efficiently, but that is partly because the customers keep their house quite cool. And I think this for me illustrates one of the issues that I think we'll kind of get to, which is that we don't, as installers, often manage to close the feedback loop. So we go to a house, we install a heat pump, the customer's hopefully happy, customer's warm, we go back, we service it, everything seems to be running okay, but without having monitoring. Now, you can monitor heat pumps, obviously, but if you want to do it actually really properly, then you need to install something like Open Energy Monitor, which has a reasonable cost associated with putting that kit into the home. So a lot of these installs are going in, and we're not really getting a good picture of how well they're running. We install with our Samsung heat pumps the Homely smart thermostat. There are another number of other smart thermostats out on the market. So what that does let us do is take a look, and we will look at a few of our recent installs when it's very cold, and we'll just check whether they are running at the flow temperature that we would expect them to be running at. Because when you design a heat pump, you're designing it for a specific design temperature outside. So around here, that's often about -2, -3, and also a specific flow temperature on that cold day. So depending on the house, we might be on an older house, we might be doing that at 50, trying to get that down to 45. So if I've done the design and it's come out that at -3 outside, then we would expect the heat pump to be running at 50 degrees, say. It's really useful to be actually able to go back and check that you're achieving that, because if you've oversized the heat pump, actually the flow temperature will be an awful lot lower. If you've undersized the heat pump, you will know about it because your customers will be cold. So yeah, I think it's that oversizing that's actually harder to find out if you've done that or not, if you don't have the data to go back and take a look. So yeah, that's all from me.
Thank you, Leah. That was great. So I've got a few bits of extra info, and then we'll get on with some Q&A, which will be really good fun. So some further information, if you want to hear me talk even more about heat pumps and oversizing, there was this podcast I did a couple of years ago. So you could have a look on that if you're not sick of me already. We've got these training dates coming up. So U-Value training, level 1, you can read it there. Training for all the different products. Here's some dates. Come up to BTS HQ and be trained in the room I'm in now. And a few diary dates. We're going to be out and about on the road. So if you want to come and see the kits, have a chat with us. We've got a good bit of country coverage over the next little while. So you can come and see us at any of these events. And that would be really nice to meet in person. And the next webinar, we're super busy in May out on the road. So we're actually taking a break during May, and the next one will be at the start of June, and it will be measurement in action, some nice case studies of performance measurements in different applications, and that'll be with Michael. So thanks so much for listening to the presentation part. Leah, I'm going to hijack the questions just for a couple, because there's a couple of burning questions I'd like to know. I won't rob too much time from everyone else. So for me, I'm super into heat loss measurement, and therefore right sizing seems important to me. But I also can completely appreciate that it's not by any means the only part of a heat pump install, or perhaps even the biggest part of it. So how much do you worry about it? If you was a sort of a top of the pops, the biggest things you're going to worry about a good install, where would it score?
Like anything, it depends on the house. So if we're doing smaller, more straightforward homes that are newer, we feel pretty confident that we can get a good enough heat loss calculation done. It's more about unusual homes, larger homes, homes where you've got specific constraints. I mean, quite often what we'll do is we will do the heat loss calculation conventionally, and then if there's questions that are thrown up, so for example, we can't find anywhere to put the heat pump because it's too big, or the sound calculation causes us an issue, or it's a really large house and you need potentially 2 heat pumps, then those are the times that we're going to say, right, okay, let's do some measurement here. Yeah, so it's often a kind of a response to what we find in the initial heat loss calculation. So yeah, it is a concern, but there is cost associated, of course, time and cost with doing the measurement. So if it's a pretty straightforward smallish house, smallish heat pump, then we don't worry too much. Yeah, just for practical reasons, really.
Yeah. Just because I love it, right? I shared that field trial of 80 houses, and 68% of them were getting the wrong size heat pump. So honestly, my experience is that all of these houses are different. But what's not persuasive about that?
It's time and money. I mean, people are spending a lot of money on a heat pump already, and people want it to be straightforward and quick and cheap. And as a company, we don't tend to deal with an awful lot of those kind of jobs. We tend to pick up the more complex, larger, less cheap work. So I think we probably lean into the whole measurement thing a little bit more. If you're just trying to get out a volume of heat pumps installed, then you don't. And I guess there's the seasonality factor as well. I can't only sell heat pumps in the winter. That would be a bad business. So it is easier to do the data logging and things in the winter. I don't know if you could just perhaps whiz through which of the measurements are possible in the summer and which can only be done in the winter. That might be helpful.
Yeah. So air tightness measurement, you could do any time and ventilation flow rate measurement. U-value measurements, you need a temperature difference. So, I mean, in this country, it means winter only. We've got a few customers in Saudi Arabia, and they're never getting a temperature difference where it's warmer inside, but not really relevant for us. And then for HTC measurements, it either the data has to be from during winter, but if you're using Smart HTC Go, you could be using historical. All smart meters have 13 months of history on board. Suddenly loses confidence that the right number is 13 months, but it's just more than 12 months, it's absolutely certain. So you can go back into the previous winter and use that data at any time. Yeah. And then one more question. Do you think that right sizing, particularly oversized, I'm asking here, has a big impact on running efficiency? Or for me, there's not been any totally convincing massive study that demonstrated yay or nay on.
No, and it does depend very much on the heat pump. So I find it a little bit strange that heat pump manufacturers don't make it super clear. You have to dig into their data a little bit to try and understand what their sort of minimum turn down is. So, for example, a heat pump manufacturer may have I don't want to pick on any manufacturer, but they might have a 5 kilowatt unit, an 8 kilowatt unit, a 12 kilowatt, and a 16 kilowatt. Now, with some manufacturers, those two of those pairs of units are actually more or less the same unit. They just have some slightly different software and components to make them into the slightly higher or lower. So they are going to have, all those units are going to have a sort of a minimum floor that they can get down to, and that varies massively between heat pump manufacturers. So really, you want to have that kind of data to hand, but it's actually quite difficult to find. Some heat pump I'm not going to name any names, but some heat pump manufacturers do it better than others. So if you've got a heat pump that can comfortably work at 10 kilowatt and can ramp right the way down to 2 kilowatts, then you haven't got so much of an issue. And I mean, the thing to remember as well is that heat pumps are ramping up and down all the time anyway. So where we're talking about a heat loss calculation, we're talking about what's the very, very hardest that the heat pump is going to have to have to work. And last week, for example, the heat pump will still have been running, but it will no way have been running at its full capacity. So heat pumps are always shifting their output. The tricky times for efficiency are the shoulder months, actually, around now, when people do still want some heat. It does still get a little bit colder overnight, but yet you're not really asking very much of the heat pump at all. And you want it to be able to just tick over at a low level. And the problem is that if you can't get down to that low enough level, you get the on off. But it definitely needs some proper, more than just anecdotal evidence, some proper kind of analysis and measurement.
I'll have to remain slightly equivocal when I say it then.
Yeah, I think the biggest things are more about getting the right number of radiator upgrades and making it a viable prospect for people, not putting in 2 heat pumps where 2 heat pumps weren't really needed, those kind of things.
Mm-hmm. Super.
Fantastic. Thank you very much. Richard, there were some really useful questions, and hopefully will lead nicely into the questions that have come in through the session as well. I will try and go through them in the right order, so that we don't lose the flow too much. The first one is aimed at Richard. Have you examined any correlations between the homes you've measured that were all very similar in terms of measured HTC, annual gas use, and internal temperature? Appreciate heating system efficiency and gains would have big impacts, but wondered if there could be some correlation.
Short answer would be no. It gets really difficult to compare HTC measurements because there's so much going on in them. You have, even if they've got similar gas consumption, the houses could be totally different. So you could have a massive, really well insulated house that's got a lot of heat loss by virtue of being enormous, with some large south facing window. And then you could have a tiny, not very well insulated house without a lot of solar gains. And so they're so dissimilar to each other that it becomes really difficult to do comparisons. And also, weather is really confounding for comparing heat loss measurements, because when it's cold, it's usually in winter here, it will be clear, and you get quite a lot of solar gains during the day because the sun's at a really low angle, so you get quite good access to windows. But you get a clear sky at night, and that is really cold radiatively. So basically, you start off thinking, I'm going to do a simple comparison, and all of a sudden it sort of fritters off into massive complexity, and it's hard to draw a lot out of it. That was way more building physics than they're asking for.
That's all right. I think that may well carry on in a moment. Next question is from Sophie. What options are there if the HTC only works through the winter? How can we measure more effectively if designing in the summer?
Yeah, it's a big practical challenge for us, actually. That's why we did Smart HTC Go primarily. 2 reasons. 1, that, and 2, we found a lot of people either had energy data or temperature data, so it was difficult to bring them together. So I already said Smart HTC Go, you could use it based on historical data, and then you can still do the air tightness and the ventilation flow rate. I might be totally misguided, but I think a lot of heat pump journeys are several months long rather than several weeks long. So I wonder whether actually a higher percentage of them run into a bit of winter than we might guess.
Yeah, absolutely. And the next question is for Leah. Was the £2,000 saving just counting the RADs, or RADs and smaller ASHP?
That was the RADs and the smaller heat pump. There's not actually a massive differential between different sizes of heat pump, but that was trying to include a rough idea of some radiator costs and the radiator install costs, and that difference.
Fantastic. Has any indication been given of what prospect there is that right-sizing heat pumps, i.e. using measurements, will be mandated for the boiler upgrade scheme and other warm homes plan aspects for the private housing sector?
May I, Leah?
Nothing that I've heard. I mean, it actually, uh, it's a bit of a funny one, because you are meant to do a heat loss calculation as an installer, and so you need to do that. But you are also allowed to show that you have made a defensible engineering-based judgment about the heat loss. So if you have done something that involves measurement and it's proper measurement, then you are, entirely allowed under MCS to use that as your basis for your heat loss, and your heat pump sizing. But you do also need to go through the process of the official heat loss calculation as well. So there is scope to do both, but you do have to do the one kind of official way of doing it as well, and set that out clearly to the customer. This is the official way. This is the measurement I've undertaken. This is why I think this is more valid. And you go from there.
I think that reflects as well that there's been consultations for literally decades about using heat loss measurements in building regulations, in eco, bus, in everything. And the Future Homes consultation, for example, had questions about that, and the responses were really very positive. But the government response was still, we're not quite going to do this yet. So I personally think that a lot of the time regulation follows use rather than the other way around, and maybe that's fair enough. And I think what we're talking about here are clear benefits from right sizing that hopefully wouldn't need to be mandated to be used, and that if they were picked up and used more regularly, and therefore we understood how they fit in with how an install works more easily, they'd be more likely to be mandated. So it's always difficult to know which is the cart and which is the horse and which way around it's going to go. But it's a sort of more positive situation than, for example, EPCs, because the guidance is written that you are allowed, as Leah just said, to make a reasoned judgment and use the measurements. In EPCs, it's much more locked down, and air tightness is the only thing you can put in.
I think one thing that would be interesting, if anyone is involved in kind of policy areas to explore, is that I know there's been talk with DESNZ about can we agree a sort of one that somebody would go in and do a heat loss survey that could then be passed to different installers. And we've been consulted that as an installer group within MCS, and we very much pushed back on that and said, well, no, actually, we need to do the survey, we need to see the house, we need to look at a whole load of other things as well as the heat loss calculation. So actually, by kind of having a survey done up front, you don't necessarily win that much. But there is, I think, an argument for having measurement done up front, so that people could kind of have a heat pump passport, if you like. I've had these measurements done. I've had my smart meter data looked at. This is what I know in terms of the heat loss calculation. Of course, that gets us out of the seasonality issue somewhat as well, because somebody could do that way ahead of actually wanting to have a heat pump installed. Because I know it's a frustrating consumer experience when you get told to go and get 3 quotes and you go to 3 heat pump installers, and one tells you need a 12 kilowatt heat pump, one says a 9, and one says an 8. So that is not great. I can totally see that. We tend to encourage people to get some indicative costs, all based on the same size. Speak to an installer, understand who you trust and who you kind of think you want to work with, and then just get one installer around to do the heat loss survey, because that heat loss survey is my confidence that I've installed the right heat pump, and I will stand by those measurements, that survey, whatever I've done. And we have been known to, on unfortunate occasions where it hasn't worked, go and swap heat pumps for people. Well, we've done it once. This is the only time we've had to, but we've had to swap a heat pump for free for someone. And that example I gave you with the radiator, we've gone and we've changed the radiator for free, because it's our judgment, our survey. We have to own that. But if there was some sort of basis of measurement that had gone on, and then you were able to go to 3 heat pump installers and say, okay, I know my house is a 8 kilowatt heat loss, can you give me an idea on the price? that would be a more viable way for the heat pump journey to work, I think.
Fantastic, thank you.
Tanya, I just have to say that I'm certain that Jane Wilson on this call is sitting thinking, say glowmarked.com.
Oh, without a doubt.
I want to say that.
I was not, and it's glowforhomes.com now.
That's all right.
Next question is, have you done any heat loss calcs that include MVHR, and how is it dealt with?
Yeah, so again, another bit of a tricky area. It depends on the air tightness of the house as to how much of the efficiency of the MVHR you can count towards the heat loss calculation, because you can't just assume that all the benefits of the MVHR will necessarily reduce the heat loss by the same amount. What if the customer opens the windows all the time? So we tend to be quite conservative about how much the MVHR will reduce the heat loss because we have been caught out. So yeah, that is a tricky issue, and I'm not quite sure how measurement will get you around that, because often you're sizing the heat pump before the MVHR has gone in and is operable. But yeah, you do have a number from the whoever makes the MVHR unit, what percentage of the heat loss you would expect to be recovered by the unit, but that does not necessarily equate to what the ventilation heat loss of the home would be. I don't know if you've got anything else to add on that, Richard.
I suppose even with the MVHR, you still have some infiltration, given some air movement as well. So you get that in addition to the ventilation, which you'd hope had a lot of heat recovery with it. I mean, a lot of buildings really don't have enough ventilation. So it's more like the opposite issue.
Why can't we design the heat pump for the user's preferred temperature?
We can. That is permissible. It's just that I don't know if you're referring back to the example of the couple that I talked about. They wanted the opportunity to be able to have the house warmer as they got older. So they wanted it designed to the standard temperatures, and then they have chosen to heat it less. We can design a heat pump to pretty much whatever temperature you want it to be. I guess people often have a mind to when they sell a property as well. So you wouldn't want to sell a house on, and actually we also have a mind, because then we get called up by the next people who buy the house and say, what's this piece of crap that you've installed in my house, and why doesn't it heat my house properly? Doesn't help them if you say the last lot of people only wanted it at 17 degrees.
The next question that's come in is, what was the cost overall of installing the data loggers for the test period?
The data loggers themselves, once we've bought, it's a terrible head for numbers, sorry. Once we've bought them from Build Test Solutions, don't have an awful lot of on costs. Richard, would you just remind me of the numbers on that? There's a subscription.
Yeah, a set of loggers costs £150, and you can use them as many times as you like. And if you're buying one building at a time rather than a large volume of buildings, it's £30 to BTS. The bigger cost I think would be your time to go and put them in.
Yeah, so we've used a few different types of loggers. We have used the BTS ones, which we've gone and put out, or we've got the customer to put them out. There's a fair amount of other data you kind of need to collect as well, but a lot of that you're collecting as part of the heat loss survey anyway. I will just say that we have used the Permetrics data loggers as well, which I believe build off the Build Test Solutions architecture in the background. We found those to be a very customer-friendly version of the loggers, so they are very much post-outable to the customer. Customer sets them up, customer posts them back. So that takes away the kind of labor element from our side. But from memory, I think they charge £250 per go. That's on small volumes. They might do it differently for larger numbers.
The next one is, how much potential do modern heat pumps have to throttle the demand if it proves to be lower than anticipated?
I think I covered that in a slightly vague way because it is different for all different heat pump manufacturers. So you would have to go to the installer and get the data for the actual individual heat pump that you are installing. By and large, the more expensive and better the heat pump, the more ability it has to throttle back. Cheaper heat pumps very often don't have quite as much capability.
Okay. Are there any issues with a reversible heat pump, using a heat pump to cool during heat waves as well as heat during cold weather?
I mean, heating and cooling with heat pumps is a whole different webinar, which, happy to come back and do. but yeah, in terms of sizing, the cooling load is generally greater than the heating load by quite some margin. So if you're trying to size a heat pump to cool a whole house and reverse it and heat in the winter, that probably means you have to settle for a fairly inefficient larger heat pump for your heating demand. But yeah, that's
I guess there's
an issue.
a bit of a practical issue with, we're mostly having wet heating systems, much harder to distribute cools than an air-to-air unit.
Okay, let's move on to the next one. Where BTS HTC or HTC Go have been used to guide heat pump sizing, what post-install qualitative and quantitative data is available that confirms that the predictions were correct or reasonable?
Yeah, I suppose I'd look at that another way around, in that we've done a lot of validation of Smart HTC and Smart HTC Go versus benchmark, like co-heating tests, really expensive, invasive HTC measurement methods. So I'd look at that as the way that we've proven the accuracy of the HTC measurement, and then it's not really relevant, in my opinion, to what application it's used after that, to the accuracy of the tool itself. I don't know if I've worded that very well, but did it sort of vaguely make sense what I meant?
Okay, and what advice do you offer on how to take account of aspects that might change over time, e.g. an HTC measurement carried out while wet plaster was still drying, or big changes to occupancy that might affect internal gains?
Well, the changes to occupancy and internal gains, in as I understand it, in typical heat pump design, you wouldn't, you'd be sizing the heat demand based on the building rather than taking into account a lot of internal gains. Whether that's the right thing to do or not, I think that comes back a little bit to set point temperatures as well. I think that if the heating system's really well designed, you hope it will outlive some people's tenancy in a building, so it needs to work for the next residents as well. And there was a first part of that question, which I've forgotten.
And I've gone onto a different screen to look at the other questions. Me too. So. No, I think we'll move forwards anyway, because we've got an awful lot of questions still to get through and only a few minutes left. Can either of you explain why the rule requiring an absence of wall or roof insulation recommendations in pre-installation EPCs was removed?
I can't.
No, that's probably a subject for another day.
I guess well, there's no point me guessing.
We have a question specifically for Leah. How much time do you spend citing the air source heat pump given the MCS DB regs, and how often are they ruled out as unsuitable?
I mean, it's something we can do pretty quickly when we're doing the site survey anyway, so I wouldn't say it's massively time consuming. What we tend to find is there is always somewhere to put the heat pump. The question is it cost effective, and has the customer got the appetite for the cost and possibly the digging or trenching or whatever that might be required put the heat pump somewhere, or the cost to have a more expensive but quieter heat pump. So it's very rare that we can't find anywhere for a heat pump, but it is more common that the customer says, look, I'm just not prepared to pay the extra for a quieter heat pump, or pay to have pipes put down the garden so the heat pump can be there and out of the way. So yeah, I can think of, but yeah, I'm struggling to think of one where we just couldn't find a spot. There generally is one.
Excellent. And do you know if MCS have an opinion on HTC usage?
I don't think they have an official position, but you'll see in their calculator that there's a space to put an HTC measurement. So they've generally been pretty open-minded and supportive. I think, keeping in mind what Leah said, that, you know, I don't think they set themselves up to be heat loss assessment experts, and so that they would be looking for appropriate regulation to be coming from elsewhere to sort of to stipulate the quality. And there's a CIBSE TM which we've been helping to author, which will hopefully provide some good basis for that in the near future.
I'm going to squeeze one more question in. In retrofit projects, how reliable are heat pump sizing results from IES virtual environment compared to measured heat loss, and how should discrepancies be handled?
Yeah, IES is a dynamic model, but it does the same thing where you have to put in a U value for the different components and an amount of air movement. So it is susceptible to the same issues where those underlying assumptions are really variable. So what it would be really good at compared to a static model like 12831 or SAP or HEM would be thinking about time of use. But it would have the same issues with accuracy on heat loss as any other calculation. I think, to me, it's honestly like if I came to this room, I could measure it up by looking at it and guessing, and I'd do a reasonable job. Or I could use a tape measure and measure it out, and it would be crazy for me not to do that. That's the way I see heat loss.
Thank you for joining today's webinar. If you have any further questions, please do not hesitate to get in touch. And we will see you at the next webinar, which will delve into some case studies from the front line of building performance measurement.